Hello students, let us continue our discussion on problems of current electricity, and today in this session we'll be starting with the first problem, question number 1, page number 146 from the reference that I have given. Let me write the question first. Okay, the question is as follows. Calculate the electric current when 5 into 10 to the power of 18 number of electrons flow through a conducting wire in 3 seconds. So this is the question where they are asking us to find the electric current. Okay, so I is equal to question mark. I has to be found, the current through the conductor has to be found. What is given there? They have given us the number of electrons flowing through the given conductor. So if I assume that this is the conductor, these many electrons are flowing through this conductor in 3 seconds. Okay, so number of electrons flowing is given n, right? We always represent n as number of electrons. Okay, we can also put capital N, that's also fine. Let me take capital N itself because we are going to take small n as electron density, right? So let me take capital N as number of electrons. Both are fine, small n and capital N. So n is equal to 5 into 10 to the power of 8. So these many electrons are flowing through the given conductor. What is the time that they take to go from this end to this end of the conductor? So the time that these many electrons taking is 3 seconds. Okay. Now what does the expression of current say? The simple expression of current says I is equal to dq by dt, right? Now what is this dq? Dq is the small charge that flows in a small time of dt. This is for instantaneous current, the expression for instantaneous current. Here for 3 seconds the number of electrons flowing are constant, right? So I can simply put this as q by t, total charge that flow by total time that we take. And here again we are calculating the average current, not the instantaneous current. Okay, so the average current in 3 seconds is calculated here. Okay, so I can directly write q by t. Then what is the significance of this dq by dt? Dq by dt gives us the instantaneous current at a particular instant of time. What is the current that can be calculated? And these are higher level questions, no need to bother about them. We shall discuss them when it comes to the competitive part, but nothing to worry about them this part as of the board exam is concerned. So average current q by t. Okay, right. So what is the total charge that is flowing through the conductor? We don't know. They have not given, but they have given the number of electrons flowing. Okay, and we know that q is equal to ne, right? The total charge is equal to number of electrons multiplied by charge of each electron, right? You remember that? So from the first chapter itself. So q is equal to ne divided by t. So this becomes the expression for current. I is equal to ne by t now. Okay. So is the value of n given? Number of electrons flowing? Yes, it is given. It is 5 into, sorry, it is 10 to the power of 18. 5 into 10 to the power of 18 number of electrons flowing. Charge associated with each electron, charge of each electron is 1.6 into 10 to the power of minus 19 coulomb divided by time taken is 3 seconds. Make use of calculator, and after calculating you'll get the value of current I is equal to 0.2667 ampere. Okay, so this is the current which flows through the conductor when you have 5 into 10 to the power of 18 number of electrons flowing through the conductor in 3 seconds. Clear with this? The simple expression is I is equal to q by t, average current. We don't know what is q. Q is not directly given, but they have given n value, number of electrons flowing, and we do know that q is equal to ne, right? So when q becomes equal to ne, t becomes equal to 3 from the given data, we'll get the current I is equal to 2667 ampere. Okay, easy. Okay, the second question is as follows. A copper wire of radius 0.1 millimeter and resistance 1 kilo ohm is connected across a power supply of 20 volt. Okay, this is the given data. And we have two sub questions asked here. The first sub question is, how many electrons are transferred per second between the supply and the wire at one end? Okay, it's quite simple. How many electrons? N has to be found. That's it. Okay, the second sub question is, calculate the current density. Okay, first let me write the given data. What and all is given. Radius of the copper wire is given. How much? Radius of the copper wire given is 0.1 millimeter, right? 0.1 into 10 to the power of minus 3 meter, which can also be written as 10 to the power of minus 4 meter, right? This is the radius, assuming that the copper wire has since it's the radius given, obviously the copper wire will be having circular cross section. Okay, and the resistance of the wire is also given. Resistance of the wire is 1 kilo ohm, okay, which is considerably large resistance, 10 to the power of 3 ohm. Okay, across the power supply of 20 volt. So the power supply given here is 20 volt voltage supplied to the wire. Okay, so now let me go for the first question. In the first question, they are asking us to find the number of electrons transferred. N is equal to question mark, right? Right, let us work for N now. See, number of electrons transferred between the supply per second. Okay, this is again a given data itself, per second, which means in 1 second. Okay, so N is equal to question mark when T is equal to 1 second. Okay, this is a very important factor given, which will help us in getting the value of N. Okay, so think of it, number of electrons transferred has to be found. For that we need Q, the total charge transferred, right? And if we want Q, there should be some relation which connects Q with the factors here, but there is no relation which directly connects Q with V and R, but there is a relation which connects Q and I, right? I is equal to Q by T, and we can get I using this R and V, using Ohm's law, right? So there is a way to solve this. First, getting I, the value of I, then using I is equal to Q by T, we can get Q, and using Q is equal to NE, we can get N, right? Followed? Right. So first let me work for I. Ohm's law says V is equal to IR, and hence I becomes equal to V by R. What is V given? V given is 20 volt, right? What is R given? R given is 10 to the power of 3 ohm, right? 1 kilo ohm. So current becomes equal to 20 into 10 to the power of minus 3 ampere. So we have the amount of current flowing through the given copper wire. Okay, I we have obtained. Now we do know that I is equal to Q by T, right? Average current again. So what is this Q equal to? Q equal to NE, right? Number of electrons into charge of each electron divided by T. What is our intention? Our intention is to get the value of N, right? The number of electrons flowing. So N becomes equal to, if I send T here, I T divided by E, right? I T comes here, E comes to the denominator. So N becomes equal to IT by E. Clear with this? So what is I? I is 20 into 10 to the power of minus 3. What is time? Time is 1 second, because they have mentioned particularly that electrons transferred per second. Okay, so time is 1 second. divided by charge of each electron 1.6 into 10 to the power of minus 19 coulomb. Make use of calculator, and hence after making use of calculator you will get the value of N equal to 1.25 into 10 to the power of 17. Okay, 1.25 into 10 to the power of 17 number of electrons are transferred from one end to the other end, or from one end of the supply to the end of the wire. This many electrons are transferred in 1 second. Okay, this many electrons totally. So this is an important result, the answer of first part of the question. Okay, now let us look into the second part of the question. This is 1.6 into 10 to the power of minus 19. Okay, right. So let's look into the second part of the question. Second part of the question asks a simple quantity, which is current density. Okay, which is represented by J, right? So this is the second part of the question. Now, what is the formula of J? J is given by I by A, current per unit area of cross section. I, current, do we have the value of current? Yes, we do. We have calculated it. It is 20 into 10 to the power of minus 3 ampere. Now, when it comes to this A value, see, the cross section is circular. Since the cross section is circular, the value of radius that we have from the given data is R is equal to 10 to the power of minus 4 meter, right? So we have R, which is equal to 10 to the power of minus 4 meter. This is the radius of the curvature, and hence, since it's in circular shape, area A is equal to pi R squared, right? So this becomes 3.14 into 10 to the power of R to the power of R is equal to 10 to the power of minus 4, and hence R squared becomes 10 to the power of minus 8 meters squared. Okay, this is the value of area A, area of cross section of the copper wire given. So simplifying, A is equal to 3.14 into 10 to the power of minus 8. We get the current density value J is equal to 6.37 into 10 to the power of 5. 6.37 into 10 to the power of 5 unit is ampere per meter squared. Okay, this is the final answer. This is the value of J that we require from the second part of the question. Clear? So and hence we have solved both parts of the second question. Okay, first part we calculated number of electrons flowing, N, right? In the second part we calculated J value. Clear? Right. Let us look into the next question, question number 3. Okay, the third question is as follows. A copper wire of 10 to the power of minus 6 meters squared area of cross section. Okay, area of cross section of the copper wire is given. Carries a current of 2 ampere if the number of electrons per cubic meter, okay, number of electrons per cubic meter, this is what is small n. Okay, even in the standard derivations we have considered this value represented by small n. Okay, number of electrons per cubic meter, or number of electrons per unit volume, also the way we say, is 8 into 10 to the power of 28. Okay, calculate the current density and average velocity. So now just observe here what you, and average velocity has to be found with the value of E given. Okay, so in the first place the copper wire's area of cross section is given. Okay, let me write that. Area of cross section is directly given, which is 10 to the power of minus 6 meters squared. Carries a current of 2 ampere. Current flowing through that copper wire is also given. I is equal to 2 ampere. Okay. Number of electrons per cubic meter. Okay. Number of electrons per cubic meter, if I can, has to be taken as small n, which is given by 8 into 10 to the power of 28. Okay. And what is to be calculated? Current density has to be calculated. J is equal to question mark. And the other factor which has to be calculated is average velocity. So when they ask you the average velocity, they're asking you to find drift velocity. That's it. Okay, nothing else. So basically electrons will have two types of electron velocity, you know that, right? One is random thermal velocity and the other is drift velocity. Nowhere we will bother about that random thermal velocity. Okay, and it's normally given value. It's in the order of 10 to the power of 5 meter per second. And in particularly when it comes to numerical problems, we don't bother about those values, the thermal velocity. And the other kind of velocity left is drift velocity, and we are bothered more about that velocity itself. So here the other factor which has to be found is Vd, drift velocity. Okay, now first let me take J. Quite easy. Current density J, we have solved it in the previous problem. J is equal to I by A. Area of cross section is directly given. Current is also given. 2 divided by 10 to the power of minus 6. So current density J is 2 into 10 to the power of minus 6 ampere per meter squared. Don't forget to put the units. They carry 1 mark. Okay. So this is the value of current density J. Now what else has to be found? Vd has to be found. Okay, now look, we have the value of Vd. We have to calculate the value of Vd, and what we have is the value of I, A and N. Okay, if you remember, you have to remember the formula of current expressed in terms of Vd. Okay, I expressed in terms of Vd. Remember that I is equal to N E A Vd. Okay, or we also write that as Na Vde. Okay, Na Vd. This is the expression for current in terms of Vd. Okay, what we actually need is Vd, right? So from this expression, Vd becomes equal to I by N E A. Okay, do we have the value of I? Yes, we have. Value of A? Yes, we have. N? Yes, we have. E? Yes, we have. But look at this. This formula is fine to calculate the value of Vd. But again, what is this I by A? I by A is J, right? Since we have already calculated J, we can replace I by A using J. Even if you put the value of I directly here and A directly, you will get the same answer, nothing to worry. Okay. So, but this can also be done. I by A can be taken as J, and hence the formula becomes simpler, which is J by Ne. Okay. And now I can directly put the value of J, N and E here to get the value of Vd. So Vd becomes equal to J is 2 into 10 to the power of minus 6 divided by the N value given is 8 into 10 to the power of 28 into charge of each electron is 1.6 into 10 to the power of minus 19. Make use of calculator and add and subtract the powers carefully. After doing that, you should obtain the value of Vd given by Vd is equal to it is 15.6 into 10 to the power of minus 5 meter per second. 115.6 into 10 to the power of minus 5 meter per second. You can observe here Vd is of very small magnitude, okay, very small value. Generally it is in this value itself, few millimeters, even lesser per second, okay. So this is the value of Vd, and hence we have calculated both J and Vd, okay. In the reference given, they have directly taken this formula, Vd is equal to J by Ne, okay. You don't need to memorize this formula again. This is the basic formula which you need to memorize. I is equal to NeAVd, and you can make use of this formula to get J by Ne like this, and hence you can put J, N and E and all to get Vd. Clear? Good. So next question is fourth one and is as follows. The current flowing through a conductor having electron density, so electron density and number of electrons per unit volume, both are one and the same, okay, small n value, having electron density 6 into 10 to the power of 26 per meter cube is 5 ampere, okay. So current is given, small n is given. Calculate the time taken by an electron to drift from one end to the other end of 10 meter length of it, okay. So the current, the conductor given is of 10 meter length, and now an electron has to go from one end of the conductor to the other end of the conductor, drifting away using the external supply, the voltage that we give externally, okay. It will make use of it, and it will go from positive terminal to negative terminal to the positive terminal of the battery. Now what do we need to calculate there? We need to calculate the time taken, okay, and length of the wire is given, area of cross section is also given, and charge of the electron is given, okay. First let me write the given data. Current flowing through the conductor is given, okay. I is equal to, current flowing through the conductor, I is equal to 5 ampere, right, and the electron density, small n value, is also given, which is 6 into 10 to the power of 26 per meter cube, okay. So the value of small n is also given. Yeah, time taken has to be calculated now. Now this is a basic formula from first year mechanics, where in the kinematics, the motion in 1D, we simply take velocity given by velocity is equal to distance traveled by time taken, right, or displacement by time taken. So in the same way here, look, if I say this is the conductor of length, how much is the length? 10 meter given. So now an electron has to travel from this end to this end, right? So the distance traveled by the electron is given. The length itself is the distance traveled by the electron, which is equal to 10 meter. Now if what is the velocity with which it travels from this end to this end? The velocity with which the electron travels from this end to this end is nothing but drift velocity itself, right? So that itself is the horizontal velocity, right? Rest everything is thermal, okay, random, nothing to worry about that. So the velocity with which the electron moves itself is the drift velocity, okay, Vd. So now see, using the simple mechanical equation, velocity is equal to distance traveled by time or displacement by time, okay. So what is the displacement happening here? Displacement is equal to length of the conductor. So what is the length of the conductor? 10 meter, and that length itself is the distance which has to be traveled by the electron, right? So I can write Vd is equal to L, the length, divided by time. Clear? Why I wrote Vd is equal to L by T? Simple, from the first year formula. Displacement by time. Displacement is length of the wire, T is the time taken. So from this formula, I can write T is equal to L by Vd, and hence I can get Vd. I can get T. That is what is required. But we do not have the value of Vd here, right? We don't have the value of Vd, but we can actually get the value of Vd using the given data of I and N. Okay, what does the expression of I say? I expressed in terms of Vd. Okay, same expression that we made use of in the previous problem. I is equal to N E A Vd, right? Because see, area of cross section of the wire is given to us. Okay, let me write that. Area of cross section is given, which is 2 into 10 to the power of minus 6 meters square. Charge of electron is also given 1.6 into 10 to the power of minus 19 coulomb. So now this expression will help us in getting the value of Vd. Once we get the value of Vd, we can put that value of Vd here and get the value of T. Okay, right. First, let me work for Vd now. So from this expression, Vd becomes equal to I divided by NEA. What is the current? 5 ampere. What is the value of N? The charge density or the electron density, which is 6 into 10 to the power of 26 into charge of each electron 1.6 into 10 to the power of minus 19 into area of cross section 2 into 10 to the power of minus 6. Okay, A value. Simplifying them, here we'll get Vd, make use of calculator. It is 5 divided by 6 into 10 to the power of 26, the value of N, value of E 1.6 into 10 to the power of minus 19, value of A 2 into 10 to the power of minus 6. Okay, make use of calculator and calculate it, and hence you will get Vd is equal to 2.6 into 10 to the power of minus 2 meter per second. Okay, yeah, this is the value of Vd and the value of drift velocity that we get after simplifying this into this expression I is equal to NEA Vd. Now we have drift velocity Vd. What we need is time. Time an electron takes for drifting from one end to the other end of the conductor. And from this expression, T is equal to L by Vd, right? So T becomes equal to, what is L? L is 10 meter divided by, what is Vd? The value of Vd that we have obtained is 2.6 into 10 to the power of minus 2. So after simplifying this, we get T is equal to 384 seconds. So this much time will the electron take. This much time is taken by the electron to move from one end to the other end of the conductor. Okay. In fact, this is not how the conductor looks like. Okay. If you need to visualize it properly, this is how the conductor will be looking like. It will be a small wire connected to the battery. Okay, like this. So now, this is the actual practical situation, right? Now an electron will move from negative terminal of the battery to the positive terminal of the battery. The movement of electron is from negative terminal of the battery to the positive terminal of the battery. And this entire length of the wire is given here, which is 10 meter. Okay, this entire length is 10 meter. The time that an electron takes to move from this terminal to this terminal of the battery is 384 seconds. Okay, Yeah, remember that electron always move from negative terminal to the positive terminal of the battery, and current exactly in the opposite direction. Current flows from positive terminal to negative terminal of the battery. So this is about the solution of fourth question. Okay, this question is a lengthy and at the same time interesting question. The question is as follows. Question number 5. Earth's surface has a negative surface charge density. Okay, I've written the simple surface charge density sigma. Negative surface charge density of 10 to the power of minus 9 coulomb per meter squared. The potential difference of 400 kilovolt between the top of the atmosphere and the surface results in a current of 1800 ampere over the entire globe. If there were no mechanism of sustaining atmospheric field, okay, if there was there was no mechanism to sustain this field, how much time would be required to neutralize the Earth's surface? Radius of the Earth is given. And this neutralizing does not happen. This never happens in practice because there is a mechanism to replenish electric charges, namely continual thunderstorms, lightning in different parts of the globe. Okay, so first let's understand what the scenario is. Say this is the actual scenario that we see every day. Earth is geoid in shape, closely spherical when we take mathematical formula and all. And this is a pool or an ocean of negative charge. Earth has plenty of negative charge on its surface. Okay, and the surface charge density is given. Okay, you should remember there are three kinds of charge densities: linear charge density, surface charge density, and volume charge density: lambda, sigma, and rho. Okay, what is given here is sigma. Okay, so sigma is given. What is sigma? Sigma is total charge divided by total area. Okay, remember that. Lambda is charge by length. Rho, the volume charge density, is charge by volume. Similarly, sigma is charge by surface area. First chapter. Okay, there we have discussed about this sigma. So sigma value is given 10 to the power of minus 9 coulomb per meter squared, which means if you take 1 meter square of area on the Earth's surface, then that will have 10 to the power of minus 9 coulomb of charge in it. Okay, negative charge. So I can put negative sign. So this is the surface charge density. And the potential difference of 400 kilovolt between the top of the atmosphere. We all know that our Earth is surrounded by atmosphere, different layers of it, right? And from the top of the atmosphere, so this is negative charge, and here we don't know, it's not given what kind of charge will be there on this part, or whether charge will be there or not, we don't know. But the potential difference of 400 kilovolt between this point, between the top of the atmosphere and the surface of the Earth. Okay, between the top of the atmosphere and the surface of the Earth, between these 2 points we have huge potential difference, which is 400 kilovolt. Okay, and now you have charges here, you have potential difference here. What do you expect to happen? Where and all you have potential difference and charges starts to move. If they are positive charges, positive charges move from higher potential to lower potential, right? And if they are negative charges, they move from lower potential to higher potential. So here what we expect is this negative charge on the surface of the Earth, due to the potential difference between the top of the atmosphere and on the surface. Due to this potential difference, these charges gradually should move towards the top of the atmosphere. it's a kind of leakage that should happen. Why are they leaking? Because there exists potential difference, there exists voltage for them, and hence they are leaking, they are moving. But they cannot move freely or very fluently as they move in the conductor. Why? Because what is the composition of our atmosphere? It's more of it is air, right? Air is not a good conductor for electricity. So air is um, it's a bad conductor, but again it's not perfect insulator also. So even though air is a bad conductor, air does allow, due to ionization, air does allow a certain current to flow through it. And yes, it does happen. Current continuously flows. What is current? Flow of charges. Okay, so this air, atmospheric air, allows these charges to move from the surface to the top. Okay, yes, it happens. And what is the current that we see? See, this is the uh, charge, this is the total charge moving, and 1800 ampere, okay, which may look like a large current, but when you take the entire globe, this is very small current. Okay, for the entire globe, the leakage of current, leakage of charges, or the current that we observe is 1800 ampere, okay, for the complete globe. Now, so if this is the situation, in some time what should happen is all the charges should move and deposit on the top of the atmosphere, and hence the earth should get neutralized, which means earth should become zero charged one. And hence once it becomes zero charged, once all the charges move, there will be no electric field set in the earth. Because see, here is a point on the top of the atmosphere with considerably good positive potential compared to this point. Okay, so the potential difference given is 400 kilovolt, which means that here is a point with higher potential, here is a point with lower potential. So there should be a continuous electric field set from the top of the atmosphere towards the surface of the earth, right? Higher potential to lower potential. So electric field should be set like this. Remember that E is equal to minus dV by dx, or you can keep it simple. Here is negative charge, so electric field line should be directed towards that. Okay, so if the current continuously flow and all the charges gets leaked, what is expected? This electric field will lose its strength with time and becomes zero, right? Because once all the charges gets neutralized, of the earth gets neutralized, no more potential difference, no more electric field. Okay, but what we practically observe is this electric field is steady. With respect to time, this electric field will not lose its value. It is a steady value which is maintained across the globe. So why is it so? Is the current not flowing through the air? No, current is flowing. The current is 1800 ampere. But the mechanisms like thunder, storms, lightning and all, they happen every day on different parts of the globe. Okay, so these mechanisms help in shifting the charge again from top of the atmosphere to the earth again. Okay, see, this current is due to the flow of charges from the surface. Charges means negative charge, keep that in mind. Okay, this current is due to the flow of negative charges from the surface of the earth towards the top of the atmosphere. Okay, this much current, it's continuously there, steadily there, and this current should have resulted in neutralizing the earth, but it is not happening. Earth is not getting neutralized. So there is one more opposite mechanism which is pushing the charges back into the earth surface. Okay, so which are thunder, lightning, storms and all, right? We observe them. So, and this includes the entire globe. You might say, sir, we don't see thunderstorms every day, but they are happening in some part of the globe. So they are actually pumping the electrons back into the earth. Okay, so they pump them back, and hence this steady field and this steady potential difference is maintained. Clear with the theory part? Okay, so now the question is, if uh, that mechanism, the thunder, storm, thunder, lightning, and all are not there, then in what time the whole earth would have neutralized? Okay, which means in what time will the earth lose its entire charge? Okay, yeah, that is what we need to calculate. So now what we have is potential difference given, V 400 kilovolt. Okay, which I can write as 4 into 10 to the power of 1, 2 plus 3, 5 volts. Okay, just a minute, let me rub this. Okay, so voltage given was 4 into 10 to the power of 5 volt. Yeah, this doesn't matter much for us. Okay, because see, we have to neutralize the entire earth now. Okay, so current is I is equal to 1800 ampere. So I is equal to Q by T will give us the time for the movement of charge, the entire charge from the earth surface to the top of the atmosphere, right? So for now we have the value of I. Yes, we need T, but we don't know what is Q. What is Q here? Q is the total negative charge deposited on the earth surface. How do we get that? We have sigma given, charge density is given, charge is not given. We can make use of that. Okay, so from this formula we know that sigma is equal to Q by A, right? So what does Q become equal to? Q becomes equal to sigma A, right? Is the value of sigma given? Yes, it is given, 10 to the power of minus 9. Is the value of A given? What is A here? A is the total surface area of the earth. Okay, considering earth to be spherical in shape, the surface area A becomes equal to, okay, it is 4 pi r squared, right? And radius of the earth is given, right? 6.37 into 10 to the power of 6 meter. So simplifying this here, we'll get A is equal to 4 into 3.142 into 6.37 into 10 to the power of 6 whole squared. Okay, square this first, then multiply, and hence you will have the value of area of cross section, not the cross section, sorry, the surface area of the entire earth, given by 509.64 into 10 to the power of 12 meters squared. Okay, so this is the area of the entire earth. Okay, surface area of the earth. Okay, surface area I should remember, sphere, 509.64 into 10 to the power of 12. Now if I put the value of A here, so sigma is given, sigma is 10 to the power of minus 9 into, what is A here? A is 509.64 into 10 to the power of 12. Okay, make use of calculator and get the value of Q. So the value of Q that we'll get is Q is equal to 509.64 into 10 to the power of 3 coulomb. Okay, so this is one important result. What does this value of Q say? This value of Q says gives us the total charge deposited on the earth surface. Okay, so this is the approximate charge, the total charge deposited on the earth surface, which is 509.64 into 10 to the power of 3 coulomb. Now this charge continuously leaks in the form of current through air. Okay, but the reverse mechanisms puts the charge back onto the earth surface. Clear? But if that reverse mechanism is not there, in some time all of this charge will leak into the atmosphere. Okay, all of that will be moved away, and hence the earth becomes neutralized. So in what time will the earth becomes neutralized? In what time will the earth loses this entire charge? Very simple. It is I is equal to Q by T. So from that formula, T becomes equal to Q by I, because the current is given, rate of movement of charge is given. That is what is current. T is equal to Q by I. Q is here 509.64 into 10 to the power of 3 divided by current is 1800 ampere. Simplify this using the calculator, and hence we have the value of T given by 283.1 seconds. Okay, this is the final answer, the time in which the entire earth would have neutralized if there were no reverse mechanisms. Okay, which means this is the time taken to all the negative charge of the earth to move from the surface to the atmosphere. Okay, so this current continuously goes, at the same time the reverse mechanism puts them back, so this charge almost remains the same on the earth's surface. Clear with this? Okay, here the important concept is about working out with I is equal to Q by T and Q is equal to sigma is equal to Q by A. Okay, you have to visualize it. See, whenever I say current, it's not something which goes linear. Current can also be like this. Okay, it's a sphere and a bigger sphere. The charges are flowing from smaller sphere to bigger sphere in all directions. And in that particular situation, what is the area of cross section for the charge? It's the area, surface area of that sphere itself, right? So you have to consider or visualize the motion of charge in 3D also, because whenever we have discussed the motion of charges, it was always in 1D drift. It used to drift from one direction to the other direction. Here this is also current, but the current is due to the motion of charges in 3D in all the directions, from a smaller globe from the surface of the earth to the atmosphere. Clear?